Every single time you check the weather, watch a live game, or just use GPS to find the nearest coffee shop, you're tapping into this huge, invisible network of highways that are circling our planet. But these highways, they're not made of asphalt. Nope, they are the precise, calculated orbits of thousands of satellites that literally make our modern world work. So here's a question for you. What do live sports, a hurricane forecast, and a top-secret spy satellite all have in common? I mean, they seem totally different, right? Well, the answer isn't really about the tech inside the satellite. It's all about the unique path it travels. The orbit is everything. It's what decides what a satellite can see and what it can do. So for this, we're going to start our journey way, way out there at the highest, most distant orbit. And then we're going to work our way in towards Earth. Our very first stop is a place where satellites seem to just hang in the sky, completely motionless, like they're frozen in a perfect cosmic standstill. And this is it. It's called the geostationary orbit, or GEO for short. Just try to picture this. A satellite that's basically tied to one spot on the ground by an invisible string that's almost 36,000 kilometers long. Now, it's not actually stationary, of course. It's moving incredibly fast, but its movement is so perfectly in sync with Earth's spin that from where we're standing, it looks like it never moves an inch. And to really get a sense of the incredible scale we're talking about here, these satellites are orbiting at 35,786 kilometers up. That is just an immense distance. It's almost 3 times the diameter of the Earth itself. And that very specific altitude, well, that's the secret ingredient that makes this whole thing possible. So how in the world do they pull off this standstill trick? Well, it's kind of like a perfect cosmic recipe. It has 3 critical ingredients. First, the satellite has to be parked directly over the equator. Second, its orbit has to take exactly 24 hours to go around the Earth, perfectly matching our planet's rotation. And third, it's got to be moving in the same direction that we're spinning. You get all 3 of those things just right, and bam, you've got a satellite that's locked in place over one location. And this unique stability is exactly why GEO is so unbelievably useful. Before this orbit was used, you had to have these huge antennas constantly moving to track a satellite across the sky. But now you've got a fixed target. So if you need a constant, totally unbroken connection with one part of the world, this is the orbit you want. It's the reason you can just bolt a satellite TV dish to the side of your house, point it at one spot in the sky, and never have to touch it again. It is the absolute backbone for live global broadcasting, and for those weather satellites that just stare at a hurricane as it develops over days and days. Okay, so let's leave that high orbit behind and move in much, much closer to Earth. We're talking about a completely different kind of orbit with a very specific and, frankly, a very clever purpose. This is the orbit you use for satellites that need the perfect lighting every single time. This is called a Sun-synchronous orbit, or SSO, and the whole concept is defined by one key phrase: same local solar time. So what on earth does that mean? Well, it means that every single time the satellite flies over your city, the sun will be in the exact same position in the sky. So whether it's 10:30 in the morning in Paris or 10:30 in the morning in Tokyo, the shadows on the ground below will look basically identical. Pretty cool, huh? And just look at that altitude. We've come all the way down from nearly 36,000 kilometers to this cozy little 600 to 800 kilometers. These satellites are just skimming along in what we call low Earth orbit, which gives them a much closer, way more detailed view of what's happening below. The real magic of SSO is how the orbit itself is engineered to slowly rotate. Think of it like a spinning top that also has this tiny little wobble. That wobble is perfectly timed to match Earth's year-long trip around the sun. And this small, continuous adjustment keeps the satellite's angle to the sun perfectly consistent. It's basically letting it chase the sunlight all the way around the globe. So why does all that matter so much? Well, if you're trying to track changes on the ground over time, things like deforestation or shrinking glaciers or how cities are growing, you absolutely need to compare apples to apples. Consistent lighting isn't just nice to have, it's non-negotiable. It completely removes the variable of changing shadows, which gives scientists, and as you can probably guess, spy agencies, the clearest possible picture of what is really going on down there. Okay, for our final stop, we're going to stay right here in low Earth orbit, but we're going to shift our focus. We're moving away from consistent lighting and towards maximum global coverage. This is the orbit you use when you absolutely positively need to see the entire planet. This, my friends, is a polar orbit. And just like the name suggests, the satellite travels in a path that takes it over, or at least very close to, both the North and South poles. Think of it like this. The satellite is a scanner that's just moving up and down, right? But while it's doing that, the Earth is rotating underneath it like a piece of paper. So with every single pass, the satellite gets to image a brand new strip of the planet. Now, it's worth taking a second here to clarify a really important distinction. That Sun-synchronous orbit we just talked about, it's actually a very specific, very finely tuned kind of polar orbit. So while every SSO satellite flies a near-polar route, not every satellite in a polar orbit is sun-synchronous. A lot of them are just focused on getting that pole-to-pole coverage, and they don't really care what the lighting conditions are like. Because a polar orbit eventually covers the entire globe, it is perfect for any application that requires the complete picture. This is how we get our global weather models. It's how we create those incredibly comprehensive maps of the Earth's surface. And it's how we conduct those huge scientific studies of our planet's systems, everything from ocean currents to atmospheric chemistry. All right, we have journeyed from the crazy heights of geo all the way down to the close flybys of polar orbits. So now, let's bring all three of these invisible highways together and see how they really stack up, side by side. You know, when you really boil it all down, it's this simple. Geostationary is for staying put. Sun-synchronous is for seeing the same spot in the same light over and over. And polar is for eventually seeing every single spot on the planet. And this really shows you the fundamental trade-offs you have to make when you're designing an orbit. See, to stay fixed over one point, you need that immense altitude, like GEO at nearly 36,000 kilometers. But if you want high-resolution pictures, you have to be much, much closer, like an SSO satellite. The path, whether you're locked to the equator or looping over the poles, it directly dictates what the satellite's main job is. It's always a choice between having a constant, focused view of one region versus having the ability to eventually scan the entire globe. Each orbit is really a specialized tool for a very specific job. The thing is, each of these orbits is a finite resource. They're like specific lanes on a celestial highway. And as companies and countries start launching tens of thousands of new satellites over the next few years, filling these orbits up to capacity, the real question becomes, how are we going to manage all that traffic? How will we choreograph this incredibly complex and absolutely vital dance in the sky?